Hello, and welcome to this presentation related to simultaneous equations. This is the third presentation in the lecture series. In this presentation, we're going to consider a few further practical problems that will be solved using the substitution method. There are two previous lectures. Lecture 1 related to solving simultaneous equations predominantly using the elimination method, and all equations were essentially given to us within the question. In lecture 2 we considered practical problems where we had to generate the equations from the descriptions given in the question, but again we predominantly solved these problems using the elimination method. I strongly encourage you to review these two previous presentations before reviewing the contents of this presentation. So let's consider the further practical problems presentation here, three of which are outlined on this slide. I've included the question 11 and question 12. These are contextualized questions. In the previous presentation we solved them using the elimination method. I will show you those solutions here purely for reference, but in this presentation we're going to solve them using the substitution method. I've also included question 26 from our previous presentation, the solution to which was not given in that presentation, but you were encouraged to solve this using the substitution method. So in this presentation I will show you the full work solution for question 26 using the substitution method. And here are the approximate start times related to question 11, 12 and 26, should you want to directly review these solutions, but please note these times are rounded to the nearest minute. I've also included one further practical problem stated as exercise 5x here. This is actually an extract from our previous presentation related to logarithms and exponential functions. Reading the question we'll still be able to generate two simultaneous equations, but now they'll be in the form of r is equal to a multiplied by e to the power of b divided by theta, shown enlarged here at the bottom of the slide. So solving our simultaneous equations, we will need to find the value of constant capital A here, and also the value of b in the exponent here. So as I said, I've included this as an additional problem with a slight variation in the solution as compared to the previous questions. And just note there are actually three solutions included for exercise 5x. In the first we solve using the substitution method. The next is just a slight variation on the first solution. We still use the substitution method, but within this method we actually use fractions to help solve the equations. And the final version is an alternative solution using the elimination process. We actually divide the equations to eliminate the A unknown. And here are the approximate start times related to these various solutions. Please note again, times rounded to the nearest minute. So here's question 11 from our previous presentation. On the following slide I'll show you the full work solution. Here's the full work solution to question 11 that we worked through in our previous presentation, and this was solved using the elimination method. I'll now show you how we use the substitution method to attain the same answers. Here's question 11, just to review the question for you. In 1969, a machine shop team leader and 7 machinists together earned a value of £130 per week, whilst 2 team leaders and 17 machinists together earned £308 per week. We've got to find the weekly earnings of the team leader and the machinist. So I'll briefly outline the solution using the substitution method. So I'm using notation here of capital T equates to the team leader and capital M relates to the machinist. Of course, if you prefer to use the conventional notation of X and Y, please feel free to do so. I'm just using variables that are more specific to the context of the question. So generating the first equation, we have 1 team leader and 7 machinists earned £130 per week. What I've done next is rearrange this equation in terms of T, in this case simply subtracting 7m from both sides of the equation. So T is equal to 130 minus 7m. I've called that equation 1 purely for reference. Given the information in the question, we can generate a second equation. So this time we have 2 team leaders and 17 machinists earn £308 per week. So in mathematical form, using the notation above, 2t plus 17m is equal to 308. And I've labelled that as equation 2 purely for reference. Question 11, solution continued. Repeated equation 1, equation 2 from the previous slide for reference. So now we're going to substitute equation 1, the value of t, shown here, into equation 2. I'm going to put the value of t into equation 2. So there's the value of t. And that's substituted into equation 2. So using this substitution method, that's now formed a simple equation. In other words, we have one unknown in one equation. So we can now solve for the unknown, which of course is m here. So solution procedures outlined here. We expand the bracket on the left-hand side, and we summate the like terms. So in other words, we add these two terms, 3m. And then we simply rearrange for the value of m. So in other words, to find m, we simply minus 260 from both sides of the equation and divide by 3. So m evaluates to £16 earned per week. Question 11, solution continued. Repeated equation 1 here for reference. So now to find the value of t, we simply back substitute the value of m into equation 1. Here's the value of m for the previous slide, £16, and we insert that into equation 1. So t is equal to 18. So in other words, in 1969, a team leader's weekly salary was £18, and in the same year, a machinist's weekly salary was £16. So that's the solution to question 11, solving two simultaneous equations using the substitution method. This is purely for reference. This is question 11 continued. This relates to a previous presentation relating to geometric progression, which is a formula shown here. There's a previous presentation where we derive and use this formula. And what I've done on this slide is calculated what the value of £18 in 1969 would be in 2025, so after 56 years, assuming an annual inflation rate of 5.59%. If you have seen the previous presentation related to geometric progression, I'll encourage you to review the solution shown here. But this calculation effectively shows that £18 per week in 1969 is worth approximately £379 in 2025. That assumes a constant annual inflation rate as shown. Here's question 12, extracted from our previous presentation, which was solved using elimination. Though the context of the question might be slightly unusual, it relates to an electrical installation essentially, and I've defined the term ceiling rows here purely for your reference. I'll show you the solution on the next slide. So this is the extract from the previous presentation where we solved the two simultaneous equations using the elimination method. What I'm going to do now on the next slide is to solve the same problem using the substitution method. Here's question 12, commencement of the solution. So again, reading the question, we have one installation of 8 ceiling roses and 6 plugs, having a total cost of £2, and a second installation of 12 ceiling roses and 5 plugs, having a total cost of £2.20. We've got to find the cost of a ceiling rose and a plug. So again, as with question 11, when specifying notation, capital R is the cost of one ceiling rose, so P is the cost of one plug. So same process as for question 11, we need to generate equations given the information in the question. So we're told that 8 ceiling roses plus 6 plugs cost £2. Again, I've rearranged this equation for R, so simply subtract 6p from both sides of the equation and divide by 8. So R is equal to 2 minus 6p, all divided by 8. In this case, I have simplified the equation slightly because I can divide 2 by 8, gives me a quarter or 0.25, and I can divide the negative 6 by 8, negative 3/4, or in decimal, negative 0.75p. Labelled that as equation 1 for reference, and then generating the second equation given the information in the question. This time we have 12 ceiling roses plus 5 plugs is equal to £2.20 or 2.2. That's labelled as equation 2, purely for reference. So those are two equations. We're now going to solve for the unknowns r and p. So question 12, solution continued, just repeated equation 1, equation 2 from the previous slides. So process continued, we're going to substitute equation 1, this equation here, into equation 2. So we'll put the value of r into equation 2. This is the r value here. Then we're going to expand the bracket. We're going to summate the like terms. We have the negative 9p plus 5p gives us negative 4p shown here. And then we simply rearrange the equation for p. So in this case, p is equal to 2.2 minus 3 divided by negative 4. So that evaluates to 0.2, 20 pence, of course. Question 12, solution continued. Just repeated equation 1 for reference. So now to find the value of r, we're going to back substitute the value of p into equation 1. So here's the value of p placed into equation 1. So in this case, r evaluates to 0.1 pounds, or of course 10p. So in summary, the cost of one ceiling rose, r, is equal to 10p, and the cost of one plug, p, is equal to 20p. Here's now question 26. This was stated in the previous presentation but not solved. Here we'll provide the full work solution. So the resistance, capital R, in ohms of a wire at a temperature T degrees C is given by the formula shown here. Capital R is equal to R0 multiplied by in brackets 1 plus alpha T. R0 is the resistance of the wire at 0 degrees C, and alpha is a constant. We're given the resistance is 35 ohms at a temperature of 80 degrees C, and also 42.5 ohms at 140 degrees C. The question wants us to find R0 and alpha, and also find the resistance when the temperature is 50 degrees C. The hint in the question is to use the substitution method, so that's what we will use. So the answers for R0, alpha, and the resistance at 50 degrees C are shown in the bracket here. If you want to attempt this question without further assistance, I'd encourage you to stop the presentation and do so now, but the full work solution is shown on the following slides. So question 26, here's the commencement of the solution. We're given the equation in the question to use here, and we will generate two equations based on the information stated in the question. So we have a resistance of 35 ohms at a temperature of 80 degrees C. That's the equation here on the left hand side. This would be the R value, this would be the temperature, and I've rearranged that for R0. So in other words, divide both sides by the bracketed term. So 35 divided by 1 plus 80 alpha in the bracket, labelled as equation 1 for reference. And the second equation we can generate relates to the 42.5 ohms at 140 degrees C. So again, using the format of R is equal to R0 multiplied by 1 plus alpha T. Here's the value of R, 42.5 ohms. Here's the value of T, 140 degrees C. Call that equation 2 for reference. So now we're going to solve the equations using the substitution method. So we're going to substitute equation 1 into equation 2. So here's equation 1, R0, substituted into equation 2. Solution continued. Just repeated this line for convenience from the previous slide. So solution, we're going to multiply both sides by 1 plus 80 alpha. So from this top line here, multiplying both sides by 1 plus 80 alpha, we produce this line. On next line, we simply expand the brackets. We get expansion of brackets. Then we collect like terms together. So I have all the alpha terms on the left hand side. So I've subtracted this term from both sides of the equation over here. I subtracted this constant from both sides of the equation. On next line, we summated the terms, left hand side, right hand side. And finally, we rearrange for alpha. So in other words, divide both sides by the 1500. So alpha is equal to 7.5 divided by 1500. So that's 0.005. And you have a unit of the ohm per degree C. Question 26, solution continued. Just repeated equation 1 for convenience. So now we back substitute the value of alpha into equation 1. So here's the value of alpha calculated on the previous slide. And evaluating R0 is 25 ohms. So now we have the full equation. R is equal to 25, 1 plus alpha t, which is 1 plus 0.005 t. And the final part of the question is to calculate the resistance when the temperature is 50 degrees C. So let t is equal to 50. We can calculate the value of R using t is equal to 50 here in our calculation. So the resistance is 31.25 ohms to 4 significant figures. That's the full work solution for question 26. Here's exercise 5x. Solve using the substitution method. Let's consider exercise 5x. So from a laboratory test relating to the change in electrical resistance with temperature, the following 2 points were found. Firstly, when the temperature theta of 26 degrees C, the corresponding resistance R was 3850 ohms, and at a temperature of 82 degrees C, the corresponding resistance had fallen to 650 ohms. We're informed in the question that these values fit the law R is equal to A multiplied by the exponential function raised to the power of B divided by theta. We've got to calculate constant A, which will be in ohms, and constant B, which will be in degrees C. If you think you can attempt this question without further assistance, I would strongly encourage you to stop the presentation and do so now, but the full work solution is shown on the following slides. So here's exercise 5x, beginning of the solution. As in all the questions, we're going to generate 2 equations from the information given in the question. So the first equation relates to a temperature of 26 degrees C and a corresponding resistance of 3850 ohms. So extract the information from the question: R 3850 ohms and theta 26 degrees C. Inserting these into the equation given in the question, R is equal to AE to the B divided by theta. All I've done on this last line here is rearrange the equations to make A the subject. So basically I just divide both sides by e to the B upon 26. Notice I've written that here as A is equal to 3850 multiplied by e to the negative B divided by 26. So I'm using a negative sense here to note that we're actually dividing by the exponential function. I've called that equation 1 for reference. Next we generate our second equation given the information in the question. So that's at the temperature of 82 degrees C, the resistance has fallen to 650 ohms. So R is 650 ohms, D to the temperature 82 degrees C. So again, writing in the format of R is equal to AE to the B divided by theta, that 650 is equal to AE to the B divided by 82. And I've called that equation 2 for reference. So now we're going to use the substitution method to solve for A and B. Exercise 5x, solution continued. Just repeated equation 1 and 2 from the previous slide for convenience. So now we're going to substitute equation 1 into equation 2. So this is equation 1, value of A, being inserted here. And now equation 2. And now we just manipulate the equation to solve for the unknown B. So on the next line, I simply divided both sides by 3850. On the right hand side, I've used the first law of indices to write the 2 exponential functions as this 1 exponential function. On the next line, evaluated the left hand side and simplified the exponent on the right hand side. Now, referring to our previous presentation related to solution of equations involving exponential functions, we now need to apply the inverse function to remove the e from the right hand side. So applying the natural log, the ln function, to both sides of the equation. Left hand side we have ln of the constant. And on the right hand side, the ln cancels with the e, so that equals to the actual exponent value. We now essentially have an algebraic equation to solve one unknown in one equation. We solve by rearranging. On the next line, I've just evaluated the natural log function. So to find the value of b, I simply divide both sides by this value here, and that allows us to calculate b, which is 67.7 degrees C. Exercise 5x, solution continued. Just repeated equation 1 for reference. So now we back substitute the value of b into equation 1. So here's the value of b. The rest is purely evaluation, so I'll let you review at your own pace. So A evaluates to be 284.5 ohms. So now we can state the final equation that R equals to 284.5 e to the power of negative 67.7 divided by theta. So that's applied the substitution method for solving simultaneous equations to a problem involving the exponential function. Here's exercise 5x with a slight variation in the solution using the substitution method. We commence a problem in exactly the same way, generating equation 1 and equation 2 from the information given in the question, but the solution variation in exercise 5x occurs when we're solving for constant b. Again, the solution is the same down to this line shown here, but within this solution I've actually used fractions to calculate the exponent or the power of the exponential. So just enlarging the solution here, we're essentially adding this term and this term using fraction manipulation shown at the bottom of the slide here. So we're adding fractions, of course we need a common denominator. The easiest way to find the common denominator is simply to multiply these two denominators together, so 26 multiplied by 82 gives us a common denominator of 2132. It's not the lowest, but it's the easiest to find. And then we simply say how many times does 26 divide into 26 multiplied by 82, goes 82 times. And how many times does 82 divide into 26 times 82, goes 26 times. So we can simply add up the numerators. So negative 56b divided by 2132 is the exponent. Or if we notice we can divide top and bottom by 4, that's actually negative 14b divided by 533. So that's what's been calculated here. So as I say, just a slight variation in the solution. In the original solution, we simply used decimals, and most technician students would prefer this approach. But nevertheless, I thought I would just outline this slight variation in the solution. The final value for b, of course, is exactly the same. It's 67.7 degrees C to 1 decimal place. And exercise 5x continued solution variation. And the calculation for finding constant a is essentially the same as that we used previously. Just note in this particular case, I didn't use the 67.7 to 1 decimal place, I used more decimal places. When I used the 1 decimal place value of 67.7, a calculated to be 284.5 ohms. As I say, this slight variation in the solution sequence is purely for reference. And here's exercise 5x with an alternative solution using the elimination method. I will now review exercise 5x again. Instead of using substitution, we're going to use a form of elimination. It commences in a very similar way. We generate our first equation, shown here, labelled 1, and our second equation. But instead of using the substitution process shown previously, we're now effectively going to eliminate the a variable by dividing the equations. Here's exercise 5x, alternative solution, continued. Just repeated equation 1 and 2 here for convenience. And as I said, we're now going to divide these equations. So as shown here, equation 1 is divided by equation 2. So on the left hand side we have 3,850 divided by 650. On the right hand side we have a multiplied by e to the power of b divided by 26, and that's divided by a multiplied by e to the power of b divided by 82. Note on the left hand side we just divided the numbers by 50, so 3,850 divided by 50 is 77, and 650 divided by 50 is 13. So we're just simplifying the numbers on the left hand side. I notice on the right hand side the a cancels. The a in the numerator cancels with a in the denominator to leave us with the e to the power of b divided by 26 divided by the e to the power of b divided by 82. On the next line I've applied the second law of indices here. We're dividing the same bases, the base is e, so that means we subtract the index c. And I've just shown it in a slightly more enlarged format here. So we still have e to the power of, and here's our b divided by 26, but now we're subtracting b divided by 82. On the next line we've used a common denominator, so to find the common denominator it's 26 times 82, so our top line becomes 82b minus 26b. For your reference, we've reviewed the arithmetic operations for fractions in a previous presentation. On the right hand side that now simplifies to e to the power of 56b divided by 2132. So 82 minus 26 is the 56, and 26 times 82 is the 2132. Exercise 5x, alternative solution, continued. So now we're taking natural logarithms of both sides of the equation. So on the left hand side we have ln of 77 divided by 13 from our previous slide. On the right hand side, applying a natural logarithm is the inverse operation to the exponential, so we write this down as 56b divided by 2132. And applying the ln function on the left hand side, we have ln of 77 divided by 13. Applying the ln function on the right hand side, we'll cancel this exponential to leave us with the exponent 56b divided by 2132. What we do on the next line is simply rearrange for b, so we multiply both sides by 2132, divide both sides by 56, so that leaves us with b is equal to 2132 times the ln function divided by 56. So b evaluates to 67.72359 degrees C, which of course we had in our previous solution. Now we back substitute the value of b into equation 1. Now here's equation 1 from our previous slide, inserting the value of b and rearranging for a, in other words dividing throughout by the exponential function. We find a is equal to 284.6 ohms to 1 decimal place. So there's our answer for A, our answer for B to 1 decimal place. And of course they're the same as we determined in our substitution method, shown for B here, shown for A here. I've just used more decimal places in the solution here. And here's the bibliography used to help generate the presentation. I hope this presentation has been of use to you, and as always, thank you for viewing.